Hello, I'll be presenting methodologies for email spam classification using large language models, and the original authors of this paper are listed on this slide. I am your speaker, Alejandro Della Novale. The outline for this presentation will mirror that which is implied by the sequence of sections in the original paper, that being introduction of purpose, related works, transformer architecture overview, large language models used, research methodology, research and discussion, and concluding remarks. There's a lot of email in today's world, with 361.6 expected in 2024. 45% of those emails, as of September 2022, are spam. And spam includes deception or emails that try to deceive its recipients by trying to get an action out of them. Most of the time, they try to get the recipient to click on a malicious link via the promise of some value, money, investment, of a free item. Or some of those spam emails are based on an unfounded threat, like an urgent message from your bank. However, we can agree that most of our emails are generally marketing emails that we have not subscribed to and thus get filtered to our spam inbox. And it does so through the use of spam filtering technologies based in ML and in natural language processing to automatically classify if an email if it's spam or not. These machine learning algorithms come in the form of naive Bayes, random forest, k-nearest neighbor, and support vector machine. Deep learning models, like our large language models we'll be exploring in this paper, may also be applied for email classification. But what's with this focus on large language models? Well, there's been a recent boom in LLMs ever since ChatGPT came out, especially because they've illustrated a good ability to understand a human language or natural language. Means if you can query any of these large language models, the response you get will be fairly eloquent and largely accurate to what you're asking. So we want to utilize these strengths of LLMs to classify spam, and not only classify spam emails, but give an explanation to that classification. The way we're going to pursue those explanations of classifications on our email dataset is via three methods. Zero-shot summarization using Falcon and T5, which are open source large language models. Training a long short-term classifier, and then using XAI techniques to extract the most important words that make up a class within a given email. And then method 3, fine-tuning LLM on automatically labeled data such that we improve upon the results of zero-shot summarization in the first method. Method 2 serves as a point of comparison outside the use of LLMs so that we may compare how well of an explanatory task LLMs do compared to non-LLM methods. Here, we see the highest accuracies of the previously mentioned machine learning models in the reviewed literature. Generally speaking, these algorithms are trained in the dataset of labeled emails with their class, spam or ham, and whenever you hear ham, you can think of it synonymous with just normal email. The datasets used to train these models are generally preprocessed with stop word removal and text vectorization using bag of words, TF, IDF, or word embedding modeling. Regardless, random forest scores the highest accuracy compared to the other algorithms, despite being compared on different datasets. Here are some deep learning based methods in the related literature. Deep learning models are artificial neural networks. Artificial neural networks are efficient on capturing nonlinearity, which is why our LLMs can capture the intricacies of natural language so well. And this is exemplified by the LLM scores on an Asperger's exam, which is used to measure an individual's ability to understand the context of a sentence. Here we can see that ChatGPT-4 scores a score of 4 in the Asperger's exam, which is representative of the contextual understanding of an 8-year-old. We can also see in another paper the classification F scores of LLMs on 4 datasets, being Ling, SMS, Spam Assassin, and Enron. Enron being the dataset used in our research and in this presentation. Here we can see that the FLAN T5, or a fine-tuned version thereof, scored a 97% F score on the combined 4 datasets. Now we'll go over the transformer architecture. So let's look at what makes LLMs capture the nuances of language so effectively. It's because of the transformer architecture and its self-attention mechanism. In contrast to traditional models that relied on sequential information flow, transformers empower the model to assess the entire contextual spectrum of a sequence before predicting the next token. This architecture comprises of an encoder and decoder, both subject to positional encoding, ensuring that the model captures the sequential relationship between words. The encoder plays a pivotal role in furnishing additional context to the decoder by employing the multi-head attention mechanism. This mechanism allows the model to capture different sentence structures and semantics, like adjective uses, the placement of proper nouns, grammar, and it takes in input matrices formatted as queries, keys, and values that undergo a scaled dot product operation, of which the results are linear concatenated to form an output. This output is fed into the decoder to provide the full contextual sequence context as the decoder goes through its autoregressive iterations or generations of the current word in which it is currently predicting within the sequence. It is important to get the full context from the encoder because the decoder predicts the words in the sequence one by one, and it masks the future positions of the sequence such that the decoder only attends to the words or positions that are prior to the current iteration step. This allows the decoder to produce intelligible and accurate sentences and predictions while still keeping the context of the entire sentence in mind. The transformer architecture can be pretty difficult to understand, so I'll walk through a practical workflow of an input sequence going through a transformer. Here we have our original sentence. Tom is walking his dog, Rick. The idea is to translate this English sentence into its Spanish translation. Let's walk through. Tom is walking his dog is separated into its tokens. Those tokens are then applied with a positional encoding. And then we turn each of these words into a word embedding, which then get piped into the self-attention mechanism of the encoder. The outputs of the encoder are the full sequence contextual embeddings, which are then given to the decoder after applying the positional encoding to the input sequence after the start prediction token. What follows is an autoregressive generation of words in the following sequence. Tom, Tom está caminando, and so on iteratively until we get the final intelligible Spanish translation. Tom está caminando su perro Rick. Now we highlight the large language models used in our research. In this work, we utilize Falcon and T5 models. Falcon is a transformer that only consists of the decoder, and it has 7 billion parameters. It relies on a vast amount of data to get results that are comparable to commercial LLMs like GPT-3. We also utilize the T5 encoder-decoder transformer developed by Google that has been pre-trained on the common web crawl and utilizes 3 billion parameters. These models have been fine-tuned in-house and by an external developer, Jordy Clive, on Hugging Face, where the model was originally taken from, to pursue the summarization task. Falcon was fine-tuned on Dolly and the BILSUM dataset, while T5 was fine-tuned on various summarization datasets as shown in this slide. We will now discuss the research methodology employed in this research. To reiterate, 3 methods of email classification and their subsequent explanations are as follows. We have zero-shot summarization using Falcon and T5. We have word importance extraction from a trained LSTM classifier. And we have fine-tuning on the LLMs on automatically labeled data. The dataset we use is the Enron dataset. It consists roughly of 33,000 total emails. Methods 1 and 2 undergo tokenization, while method 3 undergoes stop word removal and lemmatization when speaking about data preprocessing. The reasons why method 1 does not go any further data preprocessing is because we want to evaluate how the model performs out of the box, hence zero-shot summarization. Whereas in method 2, we're more interested in the explanations gathered from the feature word extraction from our LSTM model than the performance of the LSTM model itself. Thus, further preprocessing was deemed unnecessary. Now we detail the zero-shot summarization methodology. For the Falcon and T5 zero-shot summarization, the prompts provided to these models already have the class of the email provided. Since these are summarization models, the idea is that the model can focus less on classifying and focus more on explaining the reason for the class using the raw text of the email and the classification. Thus, the prompt given to these models are as follows. The raw text of the email. This is a phishing or normal email. Explain why. We also have method 2, LSTM feature extraction. The LSTM model was trained on 70% the Enron data, with 30% left over for validation and testing. Once training is complete, we use explainable AI methods in the form of integrated gradients via Captum's AI package to extract the word importance of the words in the raw text of the email. What results is a list of important words that can be interpreted as reasons for the given classification of a given email. Moving on to method 3, we highlight that the Enron dataset is labeled with classifications, but not explanations for those classifications. And for fine-tuning to happen, because we want our model to correctly explain the classification, we must train the outputs to some real or correct value, some real and correct explanation. So we have to automatically label the emails with those explanations. and we do so by utilizing another language model to generate word embeddings to conduct a context search on scam-like phrases. Once we get the results from the context search, they are infilled into this label template that is provided in this slide. But what do I mean by context search? As I mentioned, we utilized another model, Spacey's English Core Web Language Model, to generate word embeddings of the raw emails with dimension size 300. We also generate word embeddings using the same model on a list of common scam phrases. Scam phrases like 100% free, new business opportunity, or urgent notice, etc. We compare the email word embedding vectors to those within the list of common scam phrases via cosine similarity. The idea is if any of the words within the original email matches in cosine similarity up to 80% with any of the vectors from the embeddings of the common scam phrases list, then the word that matches with any of those embeddings from the common scam phrases list shows an intention that is anonymous, or synonymous rather, with that of a scam or a spam email. So this generates the list of words that have the highest scam intention within the original email, and then we use those lists of high scam intensive words to infill the label provided in the previous slide. And then we use that automatically labeled data to fine-tune our Falcon model. Here are some results using method 1. The Falcon model, as you can see, delves a lot more deeper than the T5 model, but both correctly summarize the context of the email given and attempt to explain the classification given by the first sentence. Remember that method 1 gives the class to the model beforehand in its prompt. This is the results from method 2. We trained our classifier and achieved the result of 98.98%. But like I said, we're more interested in the explanations. Green represents a contribution to normal, while red represents a negative contribution to normal, or a positive contribution to what makes a spam email spam. Here you can see, at least in this spam or scam email, words prescription drugs online and unsubscribe have been highlighted as indicators or explanations for the classification of this email. Here are the results for method 3, and here you can see a sample result of the top similar words to scams within a given email. These lists of common words would be templated into the label that we saw in previous slides to generate a data set that we can then fine-tune to get the results on the right. Now, different from method 1, the results from method 3 did not have the classification of the email provided beforehand, meaning method 3 fine-tuning results not only classifies if an email is spam or ham, but also gives its explanations for it. I would like to highlight that even in the case where the LLM incorrectly classifies the email, if you look at its reasoning, like words, changes current and includes free year of wheeling and transmission monthly, co-aligns with human intuition of what makes a spam email. Although This US transmission report email is classified as ham. It is not too far of a stone's throw away to understand why someone might consider this email as spam. We'll leave with some concluding remarks. We have shown that LLMs have demonstrated greater understanding of human language than any other type of model. Future work, at least in email classification, involves moving away from this template static auto labeling by varying our prompts such that the results of those prompts can result in more eloquent and less rigid explanations and responses. Although this methodology was applied to the domain of email classification, there is little in the way to apply this methodology or research to other domains, showing how generalizable LLMs can be. Thank you.